All right, so last concept in Unit 2. All right, we've gone over Newton's first law, Newton's second law, Newton's third law. We've gone over work energy theorem. We've gone over conservation of mechanical energy. And now we're going over power. Okay? The good news for you is that in regards to power, there are no calculations for you. We might do a couple today just in an activity, but you will not be asked to perform any calculations to do with power on a unit exam. Why that is, I don't understand, because the calculations for power are probably the easiest calculations in the whole unit, but for some reason they took them out. I'm asking why. Okay? All you are expected to know is what is power and kind of what applications does it have. Okay? So, obviously we'll start out with the most powerful man in Springfield. Mr. Burns. Okay? Mr. Burns. Okay? He runs the nuclear power plant. It's like a double thing. Alright, so we got to understand what power is. We need to understand the relationship between power, force, and velocity. Now, just from a kind of a common sense point of view, if something is more powerful, is it also probably more forceful? Yes, generally. Okay? And we need to learn that power relates to how quickly work is done, not how much. And that is the thing people mess up about power all the time. Okay? Power is the rate at which work is done, not how much work is done. It is possible for a less powerful machine to do as much work as a more powerful machine, provided it's given more time to do it. Okay? And sometimes we want a job done by a less powerful machine because less powerful machines can sometimes be more what? They can be more efficient. Okay? Larger, more powerful machines often introduce a lot of inefficiency because of the way they work. Right? Okay, so in many situations, the time it takes to do work is just as important as how much work gets done. Okay, so if we take these two identical 1993 Honda Civic hatchbacks, okay, yeah, they're really old. They're like, one's really like cool. It's like the Dominic Toretto, like Fast and Furious version. Okay, and this one, it's a ricer. Yeah, okay, and this one is just the one you could have bought at the showroom. Now, they can both do the same job. They can accelerate from 0 miles an hour to 60 miles an hour. This one takes about 2 weeks for that, okay? And this one can do it in like 7 seconds, okay? Or less, probably more like 5, okay? If it's like really souped up, you know, it's got the cold air intake and shift and the turbo and all that other stuff, okay? So, the normal car, about 8 seconds. This car, about 4 seconds, because it's more powerful. Okay, there's more stuff on the engine, allowing it to generate more power. Now, in getting to 60 miles an hour, which one's going to use more fuel? This one. Yeah. Okay, it's a more powerful machine. It probably has a turbo which blows fuel in at a high rate. Okay, again, making it more powerful. Right. Whereas this one here, okay, is going to consume fuel at a smaller rate and still get the car to 60 kilometers an hour, or sorry, 60 miles an hour. Right. So they can still do the same job, but the less powerful machine takes longer to do it. Right. Now, again, it's more efficient, but it takes longer. This can be applied to basically anything. All right. If I have a like 1 horsepower electric lawnmower and a 5 horsepower gas lawnmower, okay, can they both cut my lawn? No, because if I let my lawn get really, really long, the 1 horsepower motor won't be able to handle it. Okay, it'll just burn out. But in theory, if I don't let my grass get too long, they could both cut my grass. Okay, but will it take me a lot longer to do it with the electric one? Yes. Okay. A more powerful machine will do it faster. Okay? If you have a hair dryer, if you have 2 hair dryers, one's 1100 watts, the other's 1500 watts, okay? Which one will dry your hair faster? The 1500 watt one. Okay? Incidentally, watts are the unit for power. Okay? A watt, okay? A watt is a joule per second, because power is work divided by time. It's the rate at which work is done. Okay, so a watt is a joule per second.
Can you tell which one's working with watt?
Well, because this one's all units. and I'll do this. I'll be nice. Yeah, because you would never write a formula with just units in it. Okay. Right, so this is work over time. Yeah? All right, so if I have an old-fashioned incandescent light bulb, one of the 60-watt ones, okay, that's kind of the standard one that would have been put in your house, right? How much energy does it use? 60 joules every second. Okay? Now, in modern time, we can take that incandescent 60-watt light bulb out, and we can replace it with a 4-watt LED. Okay? Now, does that 4-watt LED still light up your room? Oh, every bit as good. Same number of lumens. Okay? They would still both have about 350 lumens. Lumens is the units for light intensity. Okay? A 4-watt LED can put out just as many lumens as a 60-watt incandescent bulb. Why does a 60-watt bulb need so much more power, so much more electricity? Right? They get really hot. Incandescent means to glow because of heat. Okay? So if you ever have seen what the inside of an incandescent got the filament in it, okay? So that filament is made of tungsten, which doesn't conduct electricity very well. So we try and push electricity through this highly resistive metal. And the more resistance there is, the more the electrons are slowed down by the metal and the more heat is generated. So much heat, in fact, that the filament glows white hot and provides light to your room. But it also generates a ton of heat. You flip on an incandescent light, let it run for 10 seconds, and you can't touch it with your bare hands. Right? The bulb, the glass will be too hot. Right? You could have a 4-watt LED bulb running all day. You could reach up and unscrew it. Okay? It'll be cool to the touch because a 4-watt LED basically only puts out light energy, almost no heat at all. Okay? That makes sense to everybody? Yeah? So, work over time, okay, joules per second, or watts are our units for power. Okay? So the idea of power incorporates both the concepts of work and time. Okay? For power is the work done in a time interval. So if I'm looking at these two devices here, I've got like an old-fashioned water wheel type of generator. Okay, so water falls onto the water wheel, spins the water wheel, that turns a generator. Then I have Grand Coulee Dam, which provides the electricity for the Pacific Northwest. That would be the states of Washington, Idaho, and Oregon. Is one more powerful than the other? Okay, can this one do as much work as that one?
Yes. No.
Yes. If I run that one for 1/10 of a second and this one for 1,000 years, probably. Okay? It could probably do just as much work as this one does. All right? But that's obviously not a fair comparison. It's massive. Okay? And the other is, using a tiny bit of water. This is dammed up the Columbia River. Okay? So the entire volume of the Columbia River spills over this all the time. Okay? All right. Now, the other stuff we can derive from this, if we look at the formula for power, it's work divided by time. The other way to calculate work is to multiply force times distance. Agreed? Okay. If I have force times distance over time, is distance over time the same as velocity? All right, so I can rearrange this formula to say that power equals force times velocity as well as work divided by time. Okay? So the more forceful something is and the faster it moves, the more powerful it is going to be. Okay? So that's that relationship between force and power. The more forceful something is, the more powerful it will be. Dams just work by using the potential energy of water falling over. The water falls over and turns a turbine. Yeah? Like they're just a really big version of that water wheel. Or they have a whole bunch of those turbines in there to spin that way. Okay? All right. Now, in the metric system, like we said, we use watts as our unit for power. Okay? What's another unit for power that you've probably heard of? Amps. No, amps is current strength. It's the number of charges per second, but it's close.
Still use it for hours.
No. No, you can't. Now, volts is the potential difference. Yeah, you're thinking electrical power. I get where you're going with that. Ohms is resistance. Again, still thinking of electricity. I'm thinking like when you bought your car, they told you how many horsepower it was. Okay? Horsepower is an imperial unit for power. Okay? Because obviously the metric system wasn't around yet, okay, when that unit was invented. Now, why would we use a unit like that? Why would we use horsepower for a unit for power? Yeah. What was the internal combustion engine built to replace? Horses. Yeah. When a farmer went in and said, I have these 6 really old nags, okay, that they're too old to pull the plow anymore. How many of those motors do I have to buy to replace them? That's what they wanted to know. How many horses will that thing replace if I buy it? Will that tractor replace 6 horses? Okay, because they got to go to the glue factory, okay, because they're just old and they can't hold stuff anymore. All right, so that's what they would do. That's where the units for horsepower came from. Okay, it's an imperial unit, okay, for the amount of work that can be done by a horse in 1 second.
So would the Mexicans say they like on tablets?
No, they would still use watts. Watts is still a thing for electricity. No, they wouldn't say their light bulbs are in horsepower. Okay. However, they will use horsepower on some small appliances. Okay, garage door openers and things like that would still be rated in horsepower as opposed to watts. In fact, now at car dealerships, you can even find the power rating for cars in watts in Canada, and it's completely meaningless. Okay, because I remember when we were shopping for a car, and I went up and I looked at the sticker and it said the power rating in watts, and I'm like, is that good? I mean, I know what a watt is, but I don't know if that number is good or not. I know like 400 horsepower is good. How many horsepower is that? Because I just didn't know. It just was a meaningless number. You look at the power rating for a car in watts. Okay, if I have a blender and it's 1100 watts, I'm like, that blender can really liquefy anything. That's awesome. Okay, but when I'm looking at that number applied to a car, it just doesn't seem to, equate quite as well. All right, so we'll convert it. We'll figure out how many watts in 1 horsepower. Okay, so what essentially they did to find out how many watts in a horsepower was they hooked a horse up over a pulley to a big weight. Okay, and they made sure that if the horse could walk at 1 meter per second, okay, they could figure out his power. Because the force he would exert moving at a constant velocity would be equal to the weight here. And they knew the velocity was 1 meter per second, so it was very easy to figure out the power of a horse using force times velocity. What they found is that on average, a horse can pull 746 newtons at 1 meter per second. Okay? In other words, if you put a horse on a perfect treadmill, it could power 7.5 watt light bulbs if it was running at full tilt. Okay? Seems a little less impressive now, doesn't it? Okay? But now you can see that when you put the power of a car in watts, or kilowatts is the one I was looking at was rated, it just doesn't make a lot of sense to look at that number. Okay? Because it doesn't mean that much. 746 watts. Okay? We're looking at that number, it's this many kilowatts. Like, just tell me how many horses are parked under the hood. That's what I want to know. Okay? All right. Now, we don't have to do those calculations, so we're going to skip the calculations. And that too. Okay, now, we're going to look here at an example, okay, just kind of a little activity here that we're going to do together on power. Yeah.
Doesn't horsepower measure it differently now, or they say it's 400 horsepower, is there actually the equivalent of 400?
It can be measured, it depends how you measure it. Most of the time now they have to list the power generated at the wheels. So they put the car in a dyno, right, those resisting barrels, and they run. But for a while, some manufacturers were listing the power generated at the crank, which meant they put the engine on a machine and had it directly crank the dyno, as opposed to having the wheels crank the dyno, because a lot of horsepower is lost internal resistance between the crank and the wheels. So now it's all listed at the wheels, right, to be fair. Because most engines will produce quite a bit more horsepower at the crank. All right, now I'm going to hand out this sheet to you here, and I'm going to just explain what I want you to do with it, and then we'll go over it. Okay, so what you have in front of you guys is a quick activity to review a couple of things from this unit, introduce a little bit of stuff about power, and give a little laugh at least. Okay, so what I want you guys to do is to read through this article. Okay, I want you to do your best to fill in the blanks here. Okay, and see if you can perform any of the calculations requested. Okay, on the second page here. Okay, so they're asking you, to calculate a couple of things here. So I want you guys to see if you guys can accomplish that. So I'm going to give you a bit of time to do that, and then we'll go over it together. All right, so read it through first. Okay, then there'll be some calculations you'll need to perform, and then we'll see how we do that. Okay, so now let's walk through the rest of this here. Okay, so for filling in the blanks here, okay, first off we've got the idea that if we have Yoda, like down like by Pincher Creek, okay, where the big windmills are, okay, that he could stand there and he would, stand next to them and go, and they would go, okay? I practiced that. Okay. All right, so we've got the windmills, and they're going to rotate. This means that we don't have to have windmills in Pincher Creek. We just have to put Yoda somewhere, and he can make them spin no matter whether it's windy or not. And then that would be free energy because it doesn't cost Yoda anything to use the Force, except that it does because we saw that when Luke tried to lift the X-wing, he was tired after. So maybe it does. We don't know. But anyway, it's just a theoretical exercise about something that doesn't really exist. But that's okay. All right. So the energy that it takes to lift an object to a height is equal to the object's what times what times what? Okay, so it's mass, okay, times the acceleration due to gravity, okay, which we'll just call g, okay, times the height that it's lifted. Okay, and the X-wing scene lets us put a power limit on Yoda's peak power. So here's what we need to know. Okay, we need to know the ship's mass because we don't know that. Okay, and for some reason that's never been put into canon. Okay, there's like this thing called Star Wars canon. It's all the things that unfortunately now Disney says are true about Star Wars. Okay, and so if Disney says this is true, then it's the gospel according to Disney about Star Wars. That's what canon means. Okay, so we're going to say that the X-wing has a mass of about 5,600 kilograms. Right, that's the number that we're going to use. Okay, next we need to figure out how fast it was rising. So this guy spent like way too much time sitting in front of the TV timing how long it took the X-wing's landing strut to come out of the water. Okay, so the front landing strut rises out of the water in about 3.5 seconds. He estimates the strut to be 1.4 meters long based on a scene from the original Star Wars movie A New Hope where a person was walking under the X-wing and had to duck to get underneath it. Okay, so assuming that person would be about 1.4 meters tall when he did that. See, this guy has way too much time on his hands. Like, way too much. Okay? So we can use that then to figure out the speed at which the X-wing was rising. So we take that distance, 1.4 meters, and we divide it by the time, 3.5 seconds. What do we get there? So 0.4 meters per second is the speed that this thing is coming out of the water at. The last thing we need to know is the strength of gravity on Dagobah. That's the planet that Yoda lives on. Okay, here, so here he figures he's probably stuck because there's nowhere in the world where he's going to find the accelerations due to gravity on all the planets in the Star Wars universe except, remember how I told you there's like my level of nerdy, this guy's level of nerdy, and then like 4 more layers? Okay, there's like another layer beyond that last one. Okay, and that's where the people who make this website come in. Wikipedia. Okay, so there's Wikipedia, like that online encyclopedia. Well, Wikipedia is the Star Wars online encyclopedia. Wookiees are like Chewbacca. Okay, so this is Wikipedia instead of Wikipedia. Okay, and on there are actually the accelerations due to gravity of all the planets in the Star Wars universe, including Dagobah, whose acceleration due to gravity is 0.9 g. That means it's 90% of Earth's. So we can find the acceleration due to gravity on Dagobah by simply going 9.81 times 0.9. All right. So on Dagobah, the acceleration due to gravity is 8.8 meters per second squared, which of course makes, Yoda's lifting the X-Wing out of the swamp a little bit less impressive because it's not as heavy as it would have been on Earth. But still pretty heavy. Okay? All right, so we got 8.829. Okay, so now we can calculate the peak power output of Yoda because we know that power equals force times velocity. Okay, we can calculate the force by going m times g of Dagobah, okay, times the speed. All right, so we take our 5,600, multiply it by 8.829, and then multiply it by 0.4 meters per second. Okay, shows our speed. So times 5,600 times 0.4. All right. 19,776.96 watts is how powerful Yoda is. Okay? I mean, that's a respectable number. To be certain, it's a respectable number. Okay? All right, so that's enough power to power a block of suburban homes. Right? So like everybody on your block. Okay? It's also equal to about 25 horsepower. So you could put Yoda inside the hood of a smart car. And you could make it go like a smart car. Okay? So at current electricity prices, Yoda would be worth about $2 per hour. Not even close to minimum wage. It ain't easy being green. Okay? All right. Now, obviously we've seen in Star Wars there's other examples of people using the Force, especially when the Emperor would zap people with the Force lightning. Okay, to make electricity arc like that requires an ungodly amount of power. Okay, and that would be somewhere in the megawatt range, which is way more than the 19 kilowatts that we just saw Yoda exert. So obviously Yoda wasn't taxing himself too much, okay, in lifting the X-Wing out of the water. All right, so Yoda sounds like a good bet, okay, as an energy source, but with world electricity consumption pushing 2 terawatts, it would take 100 million Yodas to meet our demands. Okay, all things considered, switching to Yoda power would probably not be worth the trouble, or would probably be worth the trouble, but it would definitely be premium. Terrible. Okay, so let's look at what the free body diagram is going to look like here for the X-Wing fighter, because there's probably a few forces that we might have missed. All right, so we've got our X-Wing fighter, 5,600 kilograms. Okay, what are the forces acting on? Gravity.
Normal force caused by the buoyancy of the water.
Okay, the buoyant force of the water. When you're pulling it out of the water, does the water resist you? Yeah, what do we call that? Friction, yeah. It's water resistance as opposed to air resistance, but it's still friction. All right, and one big force that we're forgetting about here. The force of the force, right? Or just the force. Okay, we're forgetting about the force. Okay, and it would be an upward force, obviously, okay, in this case. So those would be some of the forces involved. Now, is the number you calculated above a reasonable estimation of the work Yoda did in lifting the X-Wing out of the water? Well, it's reasonable, but we probably didn't account for the fact that he'd had a little help from buoyancy. He'd had a little resistance to friction here. Okay, maybe that number, tweaks a little bit because of those two forces. And then number 3, this is kind of the tricky one. Assuming there's no air resistance, how much work does Yoda perform while he's moving the X-Wing horizontally? Okay, so he's doing a whole bunch of work, obviously, when he's lifting it, because he's changing its potential energy. Okay, lifting it out of the water. Then he moves it horizontally. It doesn't accelerate during that time. It just moves at a constant velocity through the air horizontally. How much work does he do? None. Okay, to move the X-Wing horizontally would require no work because it requires no energy. He isn't changing its potential energy because he's moving it horizontally. And he's not accelerating it, so he's not changing its kinetic energy. So technically, if there's no air resistance, that would require no energy and no work. Are they all right with that idea? Okay. So something a little bit different. Now we're going to look at another one kind of like this, except to do with Newton's third law. Okay, so this activity is around Newton's third law, so it's a good opportunity to review Newton's third law for your exam mark. Okay, the idea is similar to the ad that you just saw, that Let's Go ad where they reverse the spin of the Earth because that's stupid. But okay, same idea here. People always ask, well, what if we got everybody in the whole world to jump at the same time? Could we knock the Earth out of orbit?
No. Yes.
No, we can't. That's ridiculous. Okay? And the reason it's ridiculous is because the mass of the Earth is 5.98 times 10 to the 24 kilograms. Okay?
Yeah, that's pretty big.
The whole population of the Earth is a mere fraction of a % of that number. Okay? When you're looking at mass and acceleration, the force that could be exerted by people jumping is minuscule compared to the mass of the Earth. Okay? So, start of the scenario, the entire Earth's population has been magically transported to one place. Because how else would we get everybody there? Yeah, it's ridiculous. So, everybody's just in one place. Okay? The crowd takes up an area the size of the state of Rhode Island. Okay? Just like the smallest state. Okay? But it takes up an area the size of Rhode Island. So there's no reason to use a vague phrase, an area the size of Rhode Island. We're just going to say everybody's in Rhode Island, the most boring place in the world. Okay? So everybody's there. Okay? Everybody's in Rhode Island. Now, at the stroke of noon, everybody's going to jump. Everybody in the whole world. All 7 billion of us. Okay? We're all going to jump at the same time. Because, yeah, that's possible. Okay? We'll actually coordinate it so that everybody's paying attention. I couldn't get all 29 of you to jump at the same time if I tried. Okay? Yes.
All right, let's do it.
Okay. So, as discussed elsewhere, it doesn't really affect the Earth to do this. Okay? Earth outweighs us by a factor of over 10 trillion. Okay? On average, we humans can vertically jump maybe a half a meter. Okay? I mean, obviously, there's some people who are freakish athletes who can leap out of the gym, you know. But okay, on average, we'll say that everybody jumps a half a meter because that's important. If we don't, not everybody lands at the same time either. So everybody has to jump half a meter. But we're not going to include people who can't jump and babies and, you know. Yeah. Okay? So we're just going to be we're going to imagine. Okay, then everybody falls back to the ground. So if we did that, okay, even if the Earth were rigid and responded instantly, it would be pushed down by less than an atom's width. Okay? Now, technically, when everyone comes back down to the ground, a lot of energy should be delivered to the Earth because they've been up in the air, they doesn't come down, there's going to be all that potential energy turning into kinetic and doing work on the Earth. Okay? But it's spread out over the entire area of the state of Rhode Island. It's not concentrated on a single point. Okay? So it doesn't do much more than leave footprints in a lot of gardens. A slight pulse of pressure spreads through the North American continental crust. If you had a really sensitive seismometer, it might pick it up. Okay? And then it'll dissipate, and there'll be very little effect after that. The sound of all those feet hitting the ground creates a loud, drawn-out roar, which lasts many seconds, like thunder. Okay? Eventually, the air goes quiet. Seconds pass. Everyone looks around and asks, okay, why did we all do that? Okay? And there are a lot of uncomfortable glances. Somebody coughs. People start saying, I should probably go home. Okay? A cell phone comes out of a pocket. Within seconds, the rest of the world's 5 billion phones follow. Okay? All of them. Even those compatible with the region's cell towers are displaying some version of no signal. Okay? The cell networks have collapsed under the unprecedented load. Okay? Now, outside Rhode Island, all the abandoned machinery, power plants, hydroelectric dams, the stuff that runs the world is unsupervised because everybody is here. Okay? Not a good idea. Okay? Shouldn't leave a nuclear power plant unsupervised. That's like Chernobyl. Okay? So, everything begins grinding to a halt. The T.F. Green Airport in Warwick, Rhode Island handles a few thousand passengers a day. Assuming they got things organized, including sending out scouting missions to retrieve fuel, they could run at 500% capacity for years and not make a dent in the crowd getting everybody home. Okay, so we're running into some problems here. All right? So the addition of all the nearby airports doesn't change the equation very much, nor does the region's light rail system, putting people on trains and trying to get them out. Crowds climb aboard container ships in the deep water port of Providence, because we all know getting on a container ship unprepared is always a good idea. That's how people come. Yeah. Okay. So but providing sufficient food and water for a long sea voyage proves a challenge. Rhode Island's 500,000 cars are commandeered. Moments later, I-95, I-195, and I-295 become the sites of the largest traffic jam in the history of the planet. Okay? Most of the cars are engulfed by the crowds, but a lucky few get out and begin wandering the abandoned road network. It's starting to sound like The Walking Dead Season 1. Okay? Yeah, everyone's just wandering around. Okay, now, some make it past New York or Boston before they run out of fuel. Since the electricity is probably not on at this point, because nobody was looking after the plants, okay, you can't find a working gas pump. But it's okay, because there's lots of other cars. Just steal one. Because, well, the police are all in Rhode Island. What are they going to do? Okay. Now, the edge of the crowd spreads out towards southern Massachusetts and Connecticut. Okay. Any two people who meet are unlikely to have a language in common. Almost nobody knows the area. The state becomes a patchwork of chaos and coalescing and collapsing social hierarchies. Still sounds like The Walking Dead. Okay? Yeah. All right. Violence is common. Everybody is hungry and thirsty. Grocery stores are empty. Fresh water is hard to come by, and there's no efficient system for distributing it. We never even talked about the waste management problems there would have been having 7 billion people in the same place at the same time. There are just not enough porta potties anywhere. Okay? All right. Within weeks, Rhode Island is a graveyard of billions. So this whole experiment to see if everybody jumping in the same place at the same time destroys human society as we know it.
Nice.
We haven't even got to the physics part.
Evil genius.
Right. So the survivors spread out across the face of the world and struggle to build a new civilization atop the pristine ruins of the old. Our species staggers on, but our population has been greatly reduced. Earth's orbit is completely unaffected, however. That's the good news. Okay? It spins along exactly as it did before our species-wide jump. But at least now we know. All right, so here's what we're going to do. Okay? I want you guys to see if you can answer these questions. I will give you a couple more numbers. Okay? Population of the Earth. $7 billion. You'll need that. So there are 7 billion people, okay, at the site of the jump. Okay? So, we already talked about the problems with the synchronization of everybody's jump. Okay? If you've got a crowd that big, how are you going to make sure everybody's watching for your signal? You don't. And you can't just use a speaker, okay, like have a sound, because the crowd is so large that by the time the sound reached the far edges of the crowd, it could be 5 minutes later, okay, because the crowd is so big, and it goes over the horizon, okay? Remember, this is taking up the entire state of Rhode Island, right? The crowd would be so large, you wouldn't be able to see the edges of it from the middle, okay? So it would be really difficult, obviously, to time everybody's jump at the same time, right? So I want you guys to do some of these calculations here, okay, and then we'll go over them in a little bit. They're not terribly hard calculations, okay, but they're a good review of some of the calculations we'll have to do. Come on.
I would just go 7 billion.
Let's just go 7. Okay, let's walk through these here. So we already talked about number 1. Okay, now we want to calculate the total mass of the Earth's population, assuming the average mass of a person on Earth is 65 kilograms. Okay, so we're going to take our 7 billion, multiply it by 65. All right, so there's the mass of the entire Earth's population. 4.5 times 10 to the 11 kilograms. 4.55 times 10 to the 11 kilograms. All right. All right. Calculate the total gravitational potential energy of the crowd when they're at the maximum height of their jump. Mass times gravity times height. So I'm taking that number, multiplying by 9.81, and then multiplying by 1/2 of a meter, because that's how high they told us everybody was going to jump. Okay, so we have 2.23 times 10 to the 12 joules worth of potential energy when the crowd is hanging in the air at their maximum height. Now, number 4 and actually a lot of the questions hereafter sound like they require you to calculate something. But if you understand the law of conservation of energy, you realize they require no calculation at all. Because as they fall back down to the ground, their potential energy is turned into kinetic. So that's their kinetic energy when they strike the earth. Okay, so that's number 4. Now, number 5 says, the law of conservation of energy says the energy cannot be created or destroyed, but the kinetic energy of the earth will be less than that of the crowd. Explain why. Okay, they mentioned actually in there one of the forms of energy that would be produced by this, and that would be sound. Okay, they said it would sound like rumbling thunder. It would be going on for a while. So there would be some sound that represents energy. There would be some deformation of the ground. Okay, if the earth is not a perfectly rigid object, so people's feet are going to deform the ground a little bit. That's going to represent some energy that's lost. Things like that. Now, for number 6, it says determine the maximum kinetic energy of the earth as a result of the crowd hitting it. Okay, so if this was perfectly 100% efficient, how much of this number ends up as kinetic energy for the earth? All of it. Okay, there's the kinetic energy gained by the earth as a result of the crowd landing on the earth's surface. Okay, so number 7 says calculate the speed of the earth as a result of the crowd hitting it. Okay, EK equals 1/2 mv squared. I want to calculate the speed of the earth. Right? What mass do I use here? The mass of the earth. I'm trying to find the speed of the earth, not the speed of the people. Okay, the speed of the earth. So I'm going to manipulate this, and it's going to be EK divided by 1/2 times m square rooted. Okay, that'll give me V. So we'll take this number here. There we go. Square root of our answer. Okay, divided by, in brackets, 1/2 times the Earth's mass, 5.98, which I also have to bracket, 5.98 E24. Okay, there's the velocity of the Earth, or the speed change of the Earth as a result of the crowd hitting it. 8.6 times 10 to the minus 7 meters. That's approximately 8 nanometers per second. You wouldn't notice that. It's certainly not going to knock the Earth out of orbit. Okay? The moon alters the Earth's path exponentially more than that all the time as it orbits the Earth. It pulls the Earth towards it all the time. The Earth's orbit actually doesn't look like this. Okay? The Earth actually does this as it orbits the sun. Because as the moon goes around, it pulls it towards it. Okay? Other planets interact with it, pull it away. Okay? There's all kinds of things that affect the Earth's orbit as it goes around the sun. Certainly jumping or running will not do anything, okay, to the Earth.